All right, let's get started. Today is our last class. Thank you very much for coming for all of these sessions. I know it was very hard. Some of our homeworks was very difficult. It was so much of work. It was so much of work for me as well. But I hope I personally enjoyed it. I hope you guys enjoyed it too, and I hope that you guys end up using it in your research. So today, Furuk is going to talk about the spectral methods. It was part of her thesis, I guess very small part. She's going to talk about the foundation of the spectral method that she also contributed to. Please.
Thanks. Hi, my name is Foro. It's nice to be here. So today we're going to talk about spectral methods for latent variable models. And spectral methods are an alternative methods to maximum likelihood and expectation maximization for training latent variable models. And we are going to show today that spectral methods do not have the danger of getting stuck into local optima the way that EM does. And we are going to show that it's fast and scalable compared to maximum likelihood and EM. And we are also going to show that it has guarantees for correct recovery. So let's start. I'm going to focus on two topic models and show how we can use spectral methods to train them. So the first topic model is the mixture of Unigram. In general, the goal of topic models is to be able to look at documents and tell us what the underlying topics of those documents are and how are the words in the document generated, right? So in the mixture of Unigram's model, the underlying assumption is that each document is generated by a single topic. So it is a simplifying assumption, and it is not necessarily the best assumption, but we are going to start with this model. And the words in the specific topic model are assumed to be exchangeable, which means that their joint distribution of the words in the document are invariant under permutation. So if we permute randomly the words in that document, the joint probability is not going to change. And another thing that this implies is that I can model my document using this latent variable model, where we have a topic, and given the topic, all the words in the document are conditionally independent, right? So how do we generate a document under this topic model? The way we generate the document is that for each document, we are going to draw a topic, and then given that topic, we are going to randomly draw the words from a multinomial distribution. This means that I have this topic word matrix. Sorry for the handwriting. So this shows me that given each topic, I have a distribution over the words in the document. And this is the distribution that generates the word for each document, right? So let's take a look at the properties of the mixture of Unigram's model. The probability of each topic in this topic word matrix is given by Wj, right? And we have k topics in total for the corpus of documents. And we are going to show our words using the one-hot encoding. Which means that I look at the entire corpus and I construct a dictionary. And each word in the document is going to be a one-hot representation where I have a 1 at the place where the word occurs and 0 everywhere else. And the purpose of training is to be able to recover the topic word matrix as well as these probabilities Wj, right? So like I said, we can use maximum likelihood and EM to train the model and recover these parameters, and we can also use spectral methods. So let's see how we can use spectral methods. Before moving forward, let's see some tensor notation first. A tensor is a generalization of a vector and a matrix. So a matrix is a two-dimensional vector, and a tensor is a higher dimensional vector. So this is a three-way tensor here, and I use the notation A and cross 3 Rn to show this specific tensor. And this cross is the notation for tensor product. And for vectors, this just, whoa, I don't know what happened to that equation, but this is what the equation is showing. The vector product of U and V is U V transpose, right? So this vector product is going to give you a matrix. And this generalizes to higher dimensions. And if you cross multiply to a vector and a matrix, you are going to get a three-dimensional tensor, basically. And you can show a tensor by its individual components in the tensor, or you can use this cross notation that we saw here. We are going to show the pth tensor power with this cross p notation, which means that we are going to vector product v with itself p times, and we are going to get a p-way tensor, right? And this is the way I show a rank 1 tensor. This is 1. And rank k tensor. A rank k tensor can be decomposed into the vector product of p vectors. And if we have a symmetric tensor, these are going to all be equal. So we'll have the tensor power for a symmetric tensor of rank k. So let's look at the properties of the unigram, the mixture of unigrams model. Let's form the cross moment, expected value of x cross x. So what is this? This is just the expected value of x1, x2 transpose, and x1 and x2 are, say, the first two words in the document, right? And remember that we said that the words are going to be one-hot encoding vectors. So in the d-dimensional space of the dictionary, and x1 is going to be equal to ei, which is the basis vector of that d-dimensional subspace, right? And if we expand this expected value, we are going to get this summation, basically, right? So this is xi cross x1 cross x2, which is ei ej, and this is the probability of us seeing ei and ej as the first and second words in the document. And this is summed over all the words in the dictionary. Right, so what this tells us is that this expected value is just the joint probability table for seeing these words jointly, right? So this is going to be a matrix, and its ijth entry is going to give me the probability of the first word being equal to I and the probability of the second word being equal to j. Let's look at the conditional mean of each word given the topic. Remember that we said the probability of, so if we expand this expected value, we'll have the probability of the tth word being equal to I given topic j. And this is just going to be the jith entry in the topic word matrix. And summed over the entire dictionary, this is going to give me the jth column in the topic word matrix, right? So what this tells me is that given topic h, this vector is going to be the expected value of each word in the document given the topic. And the cross moment given the topic is, remember that we said that the words are conditionally independent given the topic. So this expected value can be decomposed into the cross product of each individual expected value. And we saw up here that this is mu j, so this is mu j cross mu j, right? So let's see how spectral methods comes in here for training the model. According to this theorem, the the cross moment that we formed here and we saw here can be decomposed into a rank 1 matrix, a rank k matrix whose factors or eigenvalues are the columns of the topic word matrix and whose coefficients are the probability of my h being equal to j, right? So what does this tell us? This tells us that if I am able to estimate this cross moment and then decompose it into its rank 1 components, then I am going to recover the topic word matrix and the probability of each topic, which is basically what I wanted in the first place, right? So let's take a look at the proof that is kind of not observable, but I'm going to write it down here, right? So let's expand this x1 cross x2. This is equal to the expected value of x1 cross x2 given h. So this expected value is over h, and this expected value is over x1 and x2. I don't know if you can see it. So remember that this can be decomposed. So what this is going to be is that it's going to be the expected value of x1 given h cross expected value of x2 given h. And if we open this outer expected value, we are going to get the sum of probability of seeing h equals j times this expected value of x1 given h cross expected value of x2 given h, right? And so this is exactly the form that appears here. This expected value is nothing but mu j, and this probability is nothing but wj. So that's very interesting, right? So we can estimate this cross moment from the data because everything in this expected value is observed. So we can just directly estimate it from the data. And then we decompose it into its rank 1 components. This is a non-convex optimization, but it is guaranteed to have a globally optimal solution. It is also fast and scalable, and we have an extensive linear algebra support for it. But what is the problem? The problem is that matrix decomposition is not unique in general, right? It is only unique if the factors of the decomposition are orthogonal, and the factors are separable, right?
So can I ask a question before going to the problem? So here, so we are talking specifically in the context of mixture model and a mixture of basically discrete words.
Yes.
So the idea here is that because we are assuming a mixture model and we are assuming that, let's say, there are k topics that are shared across the corpus, if we write our joint table, that the joint table is the number of co-occurrence of the words. So the green things that you're showing is co-occurrence of the words, right? So, for example, column number 1 and 5 represent number of times that the second word in the dictionary and the 5 words in the dictionary shows up. So if we compute that statistic, because of our assumption that things are in a mixture, it's going to have a low rank assumption. So my question is that, okay, so we know that has a low rank assumption, but in reality are the coefficients of these bases are mixture like pi i's, and each of these ai's are posterior of the words coming from each topics.
The columns of topic form matrix, you mean?
Yeah. So if I write expectation of xi and xj's, which is co-occurrence empirically, if I estimate it, which is like I basically make a co-occurrence, which is the number of words in dictionary versus number of words in dictionary. So because of the low rank assumption, it's going to be rank 1 is going to be mixture 1 multiplied by posterior of topic 1 by topic 2. So, but this lambda 1 should be positive, right?
Exactly.
Okay, and should be, and some lambda 1 to lambda 2. Okay.
Yeah, this should be positive.
Should sum to 1.
Yes.
Okay. How are you going to recover that?
Okay, that's a great question, and we are just about to talk about that, right? So what this means is that if the factors are not, if the coefficients are not positive and they are not distinct, and the factors, which are these columns, are not orthogonal, we are not going to be able to recover these using a matrix factorization, and rather we are going to only recover the subspace that the mu j's lie in, right? So how do we fix that?
Why is that?
Huh?
Why is that?
Because if you, so consider this one, right? If you do a rotation, then you are going to recover the same matrix. So basically, there's no guarantee that you will find these. You can find any rotation of them. You can have any rotation of them, and it still gives you the same matrix, right?
You will follow the same matrix. Ask questions.
Yeah, anything is not clear, just ask. Okay, so let me give you an example. So let me consider that I am decomposing my matrix L using the LU factorization, right? If I insert a matrix here and its inverse, this is going to be the same M, right? And this is going to be I, and the new factorization is now LS times S inverse R, right? So we are not really guaranteed to recover the exact same L and R. We can recover any rotation of the original L and R. So that's why we cannot use matrix factorization. Yeah, go ahead.
Can we think of this like this, that if the original vectors are not linearly independent, then there can be multiple eigenvalue decompositions?
Yes.
Is that it?
So there's, because of the assumption that the eigenvectors need to have need to be orthonormal, you are always going to recover that orthonormal, but it is not guaranteed for you to recover the original thing that you wanted, right? Any more questions? Okay.
Is the notion of what the vectors here and the coefficients correspond to the graphical model clear? So the vectors are basically coming from our likelihoods, the coefficients are coming from the mixture.
So let's instead look at higher order moments and see if they can help us recover the true components. Let's look at specifically the third order moment, or the third order cross moment. It can be shown again that this third order moment can be decomposed into this rank K tensor whose coefficients are the columns of the topic word matrix, and whose factors are the topic word matrix columns, and whose coefficients are the probability of your topic. And here, if you again estimate this word triplets from the document, and use any tensor decomposition to decompose it into its rank 1 components, you will recover the true components of the model, right? And the proof is basically similar to the previous one. So the way it goes is I will again use the law of total expectation to expand this. x1 cross x2 cross x3 given h, right? And because of the conditional independence, I can then write this as x1 cross, x1 given h cross x2 given h, and so on. And if we open this up, we are going to get the sum of probability of h equals j times mu j cross mu j cross mu j. Is it clear? Okay. So it turns out that the only assumption that tensor decomposition needs in order to recover the true components is linear independence assumption. So it can be used for the two other cases that matrix decomposition fail under. And this is a very milder assumption to have on your factors compared to the orthogonality condition that we needed.
Can you give like a little bit of intuition that what was the difference between input, matrix versus tensor, that in tensor case, if we decompose it into some of the rank 1 tensors, we can get it, we can have identifiability, but we didn't have identifiability.
Right. So let's look at what this is, right? This is looking at the co-occurrence probability of triplets of the words in the document. So we are using more information from the document. And I don't know if I addressed your question, but...
So I'm saying that, like, you said that in a matrix case, you can only get the subspace, but we cannot get the basis correct. But here you can get the basis.
Yes.
What is the difference between decomposition in order 2, which is matrix, versus order 3 that makes it different? Why do we have this guarantee now that we can have it back then?
That's a great question. But I don't know the answer to it.
I'm sorry, I'm just like trying to instigate the discussion. So if you go back to your tensor case.
Here.
So what would be the size of this tensor? How much memory do you need for this tensor? Yeah, this is huge, right? What is the computational?
So that's a great point. We are saying that, so yeah, exactly. So this is a D times D times D tensor, right? And your dictionary can have like 100,000 words, and that's 100,000 to the power of 3. And it is really inefficient to store this in memory. So what do we do? In practice, when we want to run this, what we do is we project this tensor down onto the k by k by k dimensional subspace. And it can be shown that, again, in that subspace, we can, the same decomposition holds, and we can recover the parameters in that subspace. And now let's see how we can project this tensor down.
Even though the tensor size is TQ, but the tensor would still be sparse, right? Because not all the words would co-occur.
Yes.
So why didn't you go about using the heuristic representation and doing the computation on the sparse tensor as opposed to having this lower potential representation?
I think there are methods that do that consider the sparsity and leverage that to make it faster. This is just one of the ways of handling this large dimensionality.
And also remember, there's an expectation. The expectations are not necessarily data sparse, because it's just enough for you to see a co-occurrence of the word, I don't know, a rare word with another rare word once, and then you have to fill that out. So an expectation probably is not data sparse. And as you go to higher order, it's going to get worse.
Another question is that how sensitive is this approach to the amount of data that you have? So my sense is that if you have this tensor, you would require a large amount of data in order to have some of the dimensions which have values.
So actually, the sample complexity is quite good. It's polynomial, so you don't need that many samples. And yeah.
Is that because the number of topics is small, but the tensor is low rank?
I don't know why that is.
Well, sample complexity is asymptotic.
Yeah.
Sure. So if you are going to tensor order like 2 and then like order of 3, so still you need to get a lot of, so that constant in asymptotic still matters. Like,
yeah. I agree. Okay, so let's see how we can project the tensor down into the k-dimensional subspace and deal with it there. So this notation means that I am multiplying matrix M2, which was, remember, it was the cross moment, with W from the left and the right. And this W is called whitening matrix. And it's going to whiten my M2 matrix. It's going to make it into an identity that has ones in the diagonal, right? And so let's assume that W is UD inverse, where U is the eigen value matrix, and the eigenvectors, and these are the eigenvalues, right? Because of the non-degeneracy assumption, which is for the factors to be linearly independent, I know that M2 is positive semi-definite. So I know that such a decomposition would exist. And I can use this W to redefine my mui's, which are the columns. And if I expand this using the representation for M2, I can see that now I get new mui's, right, that are orthonormal. And I can use this matrix W to project down my M3 tensor. So M3 tilde is defined as M3 W, 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 which means that I'm hitting M3 from 3 different directions with this matrix W and projecting it down to the K by K by K dimensional subspace. So here's one W, another W, and W, right? And okay, any questions about the mixture of unigrams model? Cool. So let's conclude this model. We saw that the raw moments in the mixture of unigrams model directly had this nice structure of the tensor that decomposed into its rank 1 components. But this is not necessarily true for all models. And in fact, the single topic assumption of the mixture of unigrams model is too limiting. And if we want to have more complex models, this analysis no longer holds. So what is a more realistic topic model? Let's take a look at latent Dirichlet allocation. Right? So under the latent Dirichlet or LDA model, you will assume that each document has a proportion of topics rather than a single topic. So for example, consider this document from New York Times. It talks about crime, it talks about sport, and it also talks about education. The number of words that are crime related might not be equal to the number of words that are education related. This is why I'll have a distribution over these topics crime, sport, and education, right? And I'll say that half of the words that I'll see are going to come from a crime-related topic. 0.3 of them are going to come from sports-related, and 0.2 are going to come from education-related topics, right? So this is exactly the assumption in LDA. The topics are generated from a topic proportion, and the words given each topic are going to be drawn from the topic word matrix. So in terms of the graphical model representation, you will have the topics drawn from the Dirichlet distribution. So each draw of the Dirichlet distribution is a probability vector, right? That sums to 1. It's on the simplex. And therefore, you can, for generating a document under LDA, you can draw a Dirichlet proportion, and for each word, you first draw the topic given the multinomial under that Dirichlet, and then you draw the words given the multinomial of that topic, right? And here's the Dirichlet distribution that underlies the topic space. It is identified with alpha. This is the parameter of this distribution. Any questions? Okay. So now let's see how spectral methods can be used for training LDA. Let's call the first order moment M1. Here we cannot no longer use the direct cross moments, and we need to find a linear combination of lower order moments and rearrange them so that the off-diagonal entries cancel out, and it gives us again that nice structure of the moment, the matrix that is decomposable, right? It is shown that this linear form of rearranging the moments is like this. So you use the first order moment and the second order moment and form this M2, and now this M2 matrix is the one that is decomposable. And if you form it and these mu i's are orthogonal, you can recover the columns of your topic word matrix as well as the parameters of your Dirichlet distribution given alpha 0. Right? Any questions? Okay, so let's take a look at the proofs here. So the expected value of x1, which was my M1, is over H. And this is given by the model. It's equal to OH, where O is my topic word matrix. And therefore, this is equal to O E of H, right? And E of H can be computed from the Dirichlet distribution because I know that the underlying distribution of H is Dirichlet. And let's look at the cross moments. X1 cross X2 is similarly expanded, and this is, sorry for the mess, this is equal to O E of H cross H O transpose. Is this clear? And we can compute O of E of X cross
What's O here?
O is the topic word matrix. We can compute the E of X, H cross H from the Dirichlet distribution. For it, we need E of H1, E of H1 squared, and E of HI, HJ. Right? And then we can replace this. We can expand M2 basically, which was E of X1 cross X2 minus 1 over, I forgot, alpha 0 over alpha 0 plus 1, E of X1 cross E of X2. You can use this and replace it in this and show that in fact it factorizes into the mu I cross mu I form.
Can you go back to your previous equation? So, on an intuitive level, can you tell me where that equation, so this alpha is the concentration parameters of the NP.
Yes.
So where does this equation come from? So you define M2, right?
Yes.
You said that I'm going to define a matrix that has expectation of the second order minus some
linear
correction.
combination. Yes, exactly.
What's the idea of coming up with this correction?
Right. So I think that first when people started doing this, they just derived this using trial and error. But the way you would go about this is you take a look at the moments of Dirichlet and try to basically compensate for the off diagonals. And if you can show that some combination of let me call this eta of this cross moment is I, or is a diagonal matrix, then you can prove that your M2 is going to have this decomposable form. So basically what you will do is you will form this, you will set the off-diagonal entries to 0, and then you will find this eta. And then you will see that eta is, eta is going to be equal to alpha 0 over alpha 0 plus 1.
So can you tell me why M2 should have this property?
M2 or E?
M2.
Why?
So why did we add this correction?
So observe that we have this E of H cross H plus eta E of H cross E of H. If you multiply this with O from the left and right, this is going to be M2, right? And so if you can show that this is basically has this nice form of whatever, that rank 1 form, I'm going to call it OJ,
so basically,
OJ, then you can show that M2 also has this nice decomposition. That's why you said the off-diagonal is 0. All the off-diagonals of this should be 0 for that.
So can I say that for this graphical model, they said that, okay, so for each of the topics for each of the topics, I can view it as a matrix, the number of topics by number of words. So this is going to be a matrix that I have to fill out. It's going to call it O.
Yeah.
And so there is a lower rank structure to this that's coming from the K topics that I have. Now, I know that it has some sort of like a low rank structure. I want to see what kind of statistic I have to come up with to recover that low rank structure. And then they reverse engineer that low rank structure. Yeah. And that low rank structure here is this form M2. So if I change the Dirichlet distribution to another distribution, that M2 that you have to come up with is different. But the nice thing about this is that you can empirically estimate M2. You can go for all of this pairwise word and you can compute all of the pair, one Hadrian expectation of that, get M1. You can compute all of the pairwise, get M2. And then M2 is just like subtraction of this. And then that's it.
So the correction for M2 is just to remove the spurious correlations?
Yeah, exactly.
So because you say that conditioned on the topic, everything would be non-correlated.
Yeah, exactly. That's how it works. And
what is the recipe would be for it general? So is it like, does it work for, so because expectation of Dirichlet as a specific for, like if I change the Dirichlet to another one.
So that's a great question, and that's what I did. So I generalized LDA to a class of distributions on the simplex. So it need not be LDA. It can be the class of normalized infinitely divisible. Basically, it's a large class of distributions that each draw of which lies on the simplex, right? And one of the special cases of normalized infinitely divisible is LDA, and you can prove for
Can you
that.
explain what normalized divisible is?
Yeah. So so NID distributions do not have a closed form in general. They are characterized with their characteristic function, and I have to
Just give a rough idea.
Yeah. So the rough idea is that so consider this.
Feel free to use whiteboard.
Simplex. Yeah.
That's
yeah. This whiteboard. Okay. So NID distributions are distributions that lie on the simplex. So consider this 2D simplex, right? The way the Dirichlet distribution is distributed on the simplex is controlled by the alpha 0 parameter, right? You can control it to move on to the vertices, or you can make it converge to the middle of the simplex by ranging alpha 0, basically, right? Other distributions of NID class have different parameters and change differently on the simplex. So that's the idea behind them. And moreover, they allow you to capture other correlations. So this one only allows you to model positively correlated topics in the document, but what if your topics in the document are not only positively correlated and have all sorts of different correlations? That's where the NID distributions come in and allow you to capture other types of correlations in your topic space, basically. And you can prove that for the entire class by doing this and setting the off diagonals to 0. You can find these eta that can correct for the off diagonal entries and extract the spectral method of doing
so. So H does not even need to come from exponential family.
No. So let's go to the third order or the form of M3 that is diagonalizable. This is now a linear combination of the third order moment, second order moments, and the first order moment of the data. And these are again simply, you can simply compute them by computing E of H cross H cross H, and linearly combining this with all combinations of the second order moment and the first order moment of Dirichlet, and setting the off diagonals to 0. And you will get these coefficients. Right? Any questions? Cool. So let's go over this again. Our goal was to recover the topic word matrix as well as the parameters of the Dirichlet distribution, and we showed that if we construct these pairwise or these statistics about the triplets of words, we can find this nice decomposition that recovers the columns of this topic word matrix for me. Right? So let's look a little bit about some practical notes when we want to compute this third order moment form. Right? So because of the exchangeability assumption, it seems that if we only use the first 3 words in the document, that's going to be enough for us to estimate this expected value. But in practice, we shouldn't do that. We should use all the words that appear in the document. And for a document of length L, well, L is big, this is not going to be efficient because I have to compute this over all ordered triplets in that document because of the exchangeability assumption. And I cannot just naively form all triplets and average over them. So what do we do? It is shown that you can use the sufficient statistic of the data, which is the word count vector, to represent each document. So let's call the word count vector with C. It lies in the D-dimensional subspace of the dictionary. And each entry of C has the frequency of the words that appear in that specific document. It can be shown that the contribution of this document to the final third order moment can be computed using this formula. And if you expand this, you can see that it is equal to this value, which is just the summation over all the word triplets in the document. And the same so for the second order moment. Right?
So can you tell me what is that coming from?
Yeah, sure. So let's take a look at the way this reduces to what. So the way this averages basically over all the word tuples. So let me. So this Cn is the word count vector, and X is the one-hot representation of each of my words in the dictionary. So if I expand the Cn is basically just summing over all the words, right? Because they are one-hot representation. So if we sum all the X's, we are going to get Cn. And we take this, we just basically expand this, and we get this form. And if we now, again, expand this, we are going to get this. And this is just my M2.
So your M2 is basically variance of the. Yeah. So Cn is your word count.
Yeah.
And it's kind of like a variance of the word count.
This is just basically
adjusted with some scale.
Yeah. No, so this is not adjusted, right? This is just for computing.
Ln minus Ln.
So this is just like for correcting for the repeats, basically, right? So yeah, when you form C cross C, this is just for the repeats of the tuples that you have across the document.
So although the quantity that I'm interested in is x1, which is probability of the first word in the document,
yeah.
Cross product with the second word, I can do that simply by just doing a simple word count.
Yeah. Right? Is it clear? Cool. And so let's take a look at some practical results comparing spectral methods with variational inference. So this was run on the PubMed dataset that has 8 million documents. And we use perplexity, which is often used in topic models, to assess how well we are modeling our data, basically, which is the expected value of, which is the e to the minus likelihood, right? Of the held out. And so this is the runtime. You can see that it's much faster than variational inference. And this is the perplexity. We can see that it is not only faster, but also results in better perplexities.
So one question is that we have seen the graph that shows this perplexity with respect to the number of the data.
Number of data?
Number of documents. This is 8 million.
Yeah.
If you have a smaller, perplexity of this is not as good as variational. So you need a lot of data to beat variational inference. So if
there is still a gap. I don't know if the gap is that large, but there's still a gap. It's still better.
So this running time is just from an empirical count, basically. Of the words.
This is the runtime of the entire training. Yeah. So let's talk a little bit about how general spectral methods are, right? So it has been shown that they can be used for training spherical Gaussians, independent component analysis, multi-view models like HMM, and correlated topic models and hierarchical topic models. But it is in general not known if it can be applied to any model, right? So if you have a new model, you have to sit down and basically come up with that compensation for off diagonals to be able to see if you can use spectral methods for a new model or not. So let's go back and conclude. We start by saying that spectral methods are are alternative methods to maximum likelihood for training latent variable models. So we know that EM has this non-convex optimization surface, and it has the danger of getting stuck into these local optima. Basically, you have to do a lot of restarts and hope that one of these restarts are going to get you to the globally optimal solution. And for spectral methods, although the optimization surface is non-convex, you are still guaranteed to get or recover the globally optimal solution under the non-degeneracy assumption. And in order to have a better comparison, EM aims to find the MLE, so it is more statistically efficient, whereas spectral method does not aim to find the MLE, so it's less statistically efficient. But EM can get stuck in local optima, like we said, and spectral methods are local optima free. EM does not have any theoretical guarantees, whereas we do have proof of consistence and for spectral methods, and we showed that it's faster than EM. But EM is easily derived for new models, whereas spectral methods is you generally don't know whether how well you can generalize this to new unseen models. Yeah.
So one question is that so this model you derive it for the case that your likelihood is producing discrete data. So this is why you can write it as a matrix.
Yeah.
What if your likelihood is continuous?
So here
like
are
a mixture, normal mixture model.
Yeah, so you can do it for a spherical mixture of Gaussians. There your goal is not to recover basically a matrix, a topic word matrix. You have other parameters to recover.
Right.
You have the what is that?
The center of the mixture.
Yeah,
and the
exactly.
variance of
Yeah.
the
So that is again a vector, a matrix. So
And
it doesn't have to do with the data being discrete. Rather, what is it from the model that you want to recover?
Well, can I do that for the case that my mixture have like a mean and the arbitrary variance?
Arbitrary? No. So I don't know the as like what is required for those to succeed, but I know that it can be applied to spherical Gaussian mixtures.
And my second question is regarding how you get the actual topic if you are actually interested in the topic. So, for example, let's say that if I want to implement this, I go and do the word count. This part is easy, and apply single value decomposition. This if it's like a second order matrix, it's just SVD, and if it's a third order, let's say that I have a procedure that gives me this low rank approximation.
Right.
So the eigenvectors of this low rank approximation can have positive and negative values. While if I want to have a topic proportion, it should be all positive and sums to 1. How can I recover that from all positive negative values?
So you want to recover so what do you want to recover? You want to recover the
so I wanted topic distribution. So the topic distribution is going to be
so you mean the topic word matrix?
Yeah.
Yeah. So this is how you recover them, right?
But if you do SVD, there is no guarantee.
Yeah. So this is not SVD, right? This is tensor. I agree that if you used M2 and mui's are anything but orthogonal and the factors are not separable, you cannot. But if you use the third order moment and your topic word matrix has full column rank, that's all you need, full column rank, or the columns are linearly independent, you are guaranteed to recover.
But in practice, when you do on M3, right?
Yeah.
If I apply my low rank decomposition on the tensor, is there
Yes.
any guarantee that
Yeah.
my new one's going to sum to 1 and it's going to be positive? And practice
Yeah.
it doesn't-
So the
doesn't
way like, so there is this like tensor power method and all these tensor decomposition algorithms that bound this to have the unit norm.
So basically I have to do that empirically. So I have to basically, when I compute, so when I apply the power method,
Yeah.
Every time give me one mu I.
Yeah.
But this mu I might be positive, negative, so I just like cut the negative values and sum, make it to sum to 1.
No, so
Because if you're applying the power method,
Yeah.
you're just like hitting the tensor with the vector
exactly.
and do it again.
Yes.
Right?
Uh-huh.
So there is no guarantee that after you hit it, the result would be non-negative. I mean, theoretically it does, but in practice does that happen?
Yeah.
What if one goes for, instead of doing, let's say, an eigen decomposition, something like a non-negative matrix factorization in tensor space? Maybe you'll end up with all positive values.
Sure, but that's not really required for tensors to have all positive values. So I don't see that being a problem.
I guess probably because if I have a matrix, let's say for simple case, if I have this matrix of all the non-negative, all like positive values, all positive. If I apply SVD, I think the only guarantee that we have is the first eigenvalue all have non-negative.
Yeah.
The second one can be terrible.
Yeah.
So that is for matrix.
Yeah.
When I have tensor,
all of them are that.
So you're saying that these in practice it actually happens.
Another thing was regarding a point about modeling continuous distributions. One could still, let's say, do a Monte Carlo approach in which you just sample from the distribution and create a matrix and then apply this method.
Well, they're trying to avoid that kind of thing. So they're trying to compute some kind of a statistic from the data that depends on the model and be done with the inference with only a few SVD.
Yeah.
Or SVD-like
Yeah.
operation. If you want to do the inference, you just run your MCMC or variation inference anyway. That was
Quick.
That was our last class. Thank you very much, and hope to see you guys in your project session. Looking forward to your presentation and posters. Thank you.